Hello students, in this video I am going to solve one problem related to adiabatic mixing in thermodynamics. So as you can see, this is the question paper of May 2019 for JNTUH. In this question paper there is a problem which is problem number 6b. So here they have given a question about the adiabatic mixing. So the question says that steam at 0.8 megapascal pressure and 250 degrees centigrade flowing at a rate of 1 kg per second passes into the pipe carrying another steam having same pressure and dryness fraction 0.9. So after mixing of these two streams, adiabatic mixing, the flow rate is 2.3 kgs per second. So what we need to do is determine the condition of steam after mixing. We need to find how is the steam after mixing of these two streams, and here the mixture is now extended in a frictionless nozzle. So the mixture after mixing, it is passed through a nozzle and it is isentropically expanded to a pressure of 0.4 megapascals. So in this problem there are two things. One is adiabatic mixing and the second part is the expansion of the mixture in a steam nozzle. Then we need to find the velocity of the steam which is leaving the nozzle. So we have to find the velocity of the steam at the exit of the nozzle. So this is the problem. One, we need to find the first thing is we need to find the condition of the steam at the exit of after mixing of these two streams. Then second is we need to find the velocity of the steam leaving the nozzle. So let's see how to solve this problem. So I have written down the same problem here, and so what is here you can see the diagrammatic representation of the problem. So here we have the first stream, second is another stream is also coming here, and these two streams will be mixing to form a totally different new set of steam. So that will be at point number 3. So how to solve this problem is, first let us take down the information given at each point. So at point 1 the pressure is 8 megapascal and the temperature is 250 degrees centigrade, mass is 1 kg per second, mass flow rate. Similarly at point 2 the pressure is same pressure, it is P2 is 0.8 megapascal, and X2, what is the dryness fraction? They have given dryness fraction as 0.9 for the steam coming through pipe 2. So X2 is equal to 0.9. We don't know what is the mass flow rate of this particular place. We don't know mass flow rate. So let me mark this is M1, so this is M2, and here is M3. So we don't know what is M2, that is one thing, but they have given the mass flow rate at this point M3 they have given as 2 kgs per second, 2.3 kgs per second. So we have to solve this to find what are the condition of the steam at this point. That means condition is generally nothing but what is the dryness fraction at that point. That is what they meant by condition. So generally when they ask for find the condition means you have to find the dryness fraction X at that point. So in order to solve this problem we will use the Mollier diagram or Mollier chart. So I'll show each point at the Mollier chart. So first let us mark the first point in the Mollier chart. So first point is we have the first point as pressure is equal to 0.8 and the temperature is 250 degrees centigrade. So I am going to mark the point which is here. The pressure is, so at pressure 8 bar. So here is your 8 bar pressure. So this is the 8 bar pressure line. So this is the 8 bar pressure line. You have 7 and you have 8 bar pressure line, and 250 degrees centigrade is the temperature. So it is going to be the P1 is 8 bar, and this your temperature is 250 degrees. So you can see that in the Mollier chart you have, these are the temperature lines, the horizontal lines. So where this 8 bar pressure is meeting the 250 degrees centigrade, so you will get the point. So this is the point where 8 bar is, this is the pressure line, this is the temperature line. So 8 bar and 250 degrees is meeting this point. So this is the first point. This is the first point. And at this point, if you look at horizontally like this, you will get the enthalpy. You will get the enthalpy at this line. So the enthalpy at this point is about 2900 some change. So here you will get this is the enthalpy. The enthalpy at this point is 2945. So at 8 bar and 250 degrees centigrade, this is incoming stream at point pipe 1. So you will get, it is coming with a 2945 kilojoules per kg enthalpy. Similarly, we can find the enthalpy at second point. So I want to find the enthalpy at 8 bar pressure and dryness fraction 0.9. So we have the 8 bar, already 8 bar is here. So this 8 bar pressure, where it is meeting the dryness fraction 0.9. So as you can see, these lines are, the slant lines are dryness fraction lines. So you have 0.9 is 0.9 is, this is the 0.9 dryness fraction line, this line. So if you extend this line where it is meeting the 8 bar pressure line, so this is the 8 bar pressure line once again. So this 8 bar pressure line is meeting this 0.9 dryness fraction. So this is your 0.2. So that means this is the place, this is the condition at which the stream is entering through the second pipe. So if you take this point, at this point you can see the enthalpy like this. Enthalpy like this. So horizontally. So you can get the enthalpy something like 2570. So this is at 8 bar pressure and x2 is equal to 0.9. So I have two things now. I have enthalpy of incoming stream through pipe 1 and enthalpy of incoming stream at pipe 2. So using these two, I have some idea about how the enthalpies are coming. Now we can find the enthalpy at point 3, that is at this point. What is the enthalpy? How to find that is, we can have an equation. We already have an equation from the adiabatic mixing that M1 by M2 is equal to H3 by minus H2 by H1 minus H3. And also we know that M1 plus M2 is equal to M3 as well. So from this equation M1 plus M2 is equal to M3, we can find M2, that is M2 is equal to M3 minus M1, which is nothing but M3 is given as 2.3 already, 2.3 kg per second, and M1 is also given as 1 kg per second. So if you subtract these two, you will get 1.3. This is the mass flow rate at point number 3. So M3 is, we have M3 now, M2. M2 is 1.3. So we have M2. So from the equation, this equation, we can substitute the values of M1, M2, M3, H1 and H2 to get the value of H3. So we can substitute those values. M1 is 1 kg per second. H1 we got it from Mollier chart. M2 is 1.3. We already just now we got it. H2 again we got it from enthalpy Mollier chart. The M3 is 2.3 and H3 is unknown parameter. So from this equation we can get H3 is equal to 2733 kgs per second. H3 is 2733 kgs per second. Now, by looking at the Mollier chart, how the H3 is meeting on which line of X, we can decide that condition of steam is about 0.98. So here is your H1, here is H2. In the middle you got H3. So that H3, whichever line of X it is cutting, that point is nothing but the condition of the steam at point 3. So that here we are getting X3 is equal to 0.98 from the Mollier chart. So now we have found the first part of the problem, that is what is the condition of the steam after adiabatic mixing. So the condition of the steam after adiabatic mixing is 0.98 dryness fraction. That is the first answer. Now let's go to the second part of the problem, that is we have to find the velocity of the exit of the nozzle. So how to find that is, we have an equation called V is equal to under root of 2 into H3 minus H4. So here H3 is already we found out. H4 is nothing but the exit of the nozzle. So first of all, let us define the nozzle here. The nozzle is getting the steam from the adiabatic mixing, which is nothing but point number 3. Now at the exit of the nozzle, we'll have the point number 4. So when the steam is leaving this nozzle, we must find the velocity. So in order to find the velocity, we have the formula V is equal to under root of 2 into H3 minus H4. So how to find the H4 is from the Mollier chart once again. Because in the Mollier chart, you can see that the nozzle is expanding the steam adiabatically. So whenever the steam is expanding adiabatically, the entropy remains constant. So using that criteria, so we can draw a vertical line from the Mollier chart. So here is my H3. So here is my H3, which is nothing but 27. We got the value of H3 is 2733. So if I take the value from this particular enthalpy line, vertical line 2733. So if I draw a horizontal line, so I'll get a point that is nothing but the H3 point. So here is my H3. So I already told you this is the H1 and this is the H2. So in between the 2 points we have the H3. Now H3, from H3 if you draw vertical line, that represents the isentropic expansion in the nozzle. So while expanding like this, we can see where that is cutting the 4 bar pressure, because they have given that after expansion the pressure is 4 bar. So while I am drawing a vertical line from the H3 point like this, I have to keep checking where it is cutting the 4 bar line. So here is my H3. So it is cutting the 4 bar line. So here is my H3. H3 is cutting the 4 bar line. This is the 4 bar pressure. So H3 to H4, I am drawing a vertical line which represents the isentropic expansion. That vertical line is meeting the 4 bar pressure line at this point. That's nothing but my H4. That is point number 4. That means that's the exit of the nozzle. So I can see horizontally like this. What is the enthalpy at the exit of the nozzle? So if we go horizontally like this on the molar chart, I can see that it is coming to this point. So the point is something like 2590. So I can get the enthalpy. Enthalpy at exit of the nozzle is 2590 kgs per kilojoules per kg. So I have now enthalpy at the exit of the nozzle. I have the enthalpy at the inlet of the nozzle, that is H3. So H3 and H4 I'll substitute in this formula. V is equal to under root of 2 into 2733, that is H3, minus H4 2590. So which is nothing but under root of 286, which comes to about 16.91 meters per second. So that is my velocity at the exit of the nozzle, which is 16.91 meters per second. So we found the second part of the question, that is the exit velocity at the nozzle exit, steam velocity at the exit of the nozzle. That's the complete solution of this adiabatic mixing problem. Thank you.